Hey, thank you, Mr. Chairman, again for the kind introduction, ladies and gentlemen. Welcome to my presentation about modeling approaches of resonant viscosity and mass density sensors. I want to start with an overview of devices we were looking at right away. From the previous talk, there's just a tuning fork missing, so we have oscillating membranes, shear oscillating platelets, straight wires, and such U-shaped wire, which again I mentioned should come close to a singly clamped structure and thus reduce cross sensitivities to temperature. All these devices can nicely be described by a lumped element oscillator, which is exposed to the sample. I'm talking about electrodynamically resonators, and what I mean with that is we excite our structures by means of Lorentz forces. So the resonators carry or consist of electrical conductors placed in an external magnetic field, and by applying a sinusoidal current, the structure will oscillate. Either we have two electrical conductors on the structure, or one. What we have is an electric conductor moving in an external magnetic field, which induces a voltage on the structure, which is our readout quantity. And in the approach for the lumped element for a lumped element oscillator, it's not really important how you read out your device. You could do it optically, capacitive, whatever. With the lumped element approach, you only have to determine from your measurement resonance frequency and quality factor, and then you can relate to mass density and viscosity. However, this approach does not, or it's hard for the lumped element approach to consider cross sensitivities and also to describe the clear electromechanical behavior. Maybe it's a little bit rough to strike this approach, but I just wanted to make you aware that the lumped element approach is not very accurate. So in this model, from now on, I will show you how to find a model for the voltage we measure on the U-shaped wire. So the U-shaped wire is nothing more than a piece of wire to which we connect to a function generator and at which we measure the voltage with a lock-in amplifier. So first what we measure is the resistance, or the thermal dependent resistance of the wire. As it makes a loop, of course, it also will show an inductance, and for calculating the inductance, we approximated this by a square, by the equation for a square loop. To verify, so at this point nothing is moving, okay? So to verify if our model for what we call offset voltage is correct, we did measurements from 1 Hertz to 100 kilohertz at 25 degrees C and at 50 degrees C in air, in isopropanol, in DI water, and in highly concentrated salt water to examine if the liquid properties would have an influence on the offset voltage. And as you can clearly see, only the temperature influences your offset. So now if we apply an external magnetic field, the thing starts oscillating, and at very low frequencies, you cannot see it here, but it's zoomed there, we have an additional peak which comes from the motion-induced voltage. So what we measure is the impedance-related voltage drop of the device plus the motion-induced voltage on the structure. And to gain viscosity and mass density from this measurement, you have to model the motion-induced voltage. We do that by considering the straight parts of the U as a singly clamped beam, and the round end of the structure is considered first to be stiff, and if we assume the magnetic field to be in parallel to the bars, we only will have excitation forces on the very end of on the round end of the beam, and also the motion-induced voltage is only on the round part of the structure. which makes modeling quite easy. So what we have to do is to find the deflection on what I call now end of the single clamp beam. So the end is the end of the straight section. And the first spatial derivative to be able to calculate the deflection at the part of the u. And with this information we can derive the velocity, and with the velocity we then can derive the motion-induced voltage. So yeah, as I mentioned, we modeled it as a single clamp beam. As excitation forces occur at the very end of this modeled beam, we can use the harmonic differential equation for a single clamp beam, which we transform to the frequency response. And all forces at the very end of the beam, so fluid forces, but also the excitation forces, are considered in the force boundary condition. And as now we have this round shape, we also will have moments, and at the end of the beam, and the moments are considered in the third boundary condition. I will talk about the moments later. So now to include the influence of the fluid on the equation of motion, we split up the mass per unit length and the damping per unit length into intrinsic mass per unit, in the intrinsic quantities, and the quantities coming from the liquid loading. We apply the well-known equation for an oscillating cylinder, for which we do a Taylor series expansions of first order, and then we get these two terms for the liquid loading of the liquid loading for the inertial and the dissipative term. And at this point, I want to make you aware that both mass density and viscosity influence the inertial term and the dissipative term. This becomes important later in my talk. Now back to how to calculate the moment. So what we do for the round edge for calculating the excitation forces, we transform these forces to the second coordinate system here, to the xi-axis. And now to calculate the associated moments urging from the forces, we have to find the center of forces. And for finding the center of forces, we do not have nothing more to do than solving this integration. For example, in this case, for the excitation force, what we have here, this is the excitation force per unit length transformed to the xi-axis of the second coordinate system. Yeah, and by solving this equation for xi-c, you will have the center of forces, and then you can calculate the momentum, which is necessary in the third boundary condition of the model. Yeah, and for the inertial and fluid terms, of course, the relation is identical, but the solution is different. To consider the cross sensitivity to temperature, we assume linear thermal expansion of the device, which should be valid because our temperatures, in best case, would be from 0 degrees C to 100 degrees C, and for thermal expansion, this is still a very narrow temperature range. And we also consider the thermal change of the Young's modulus. Now let me show you a comparison of measurements and models. So this are evaluated quality factors over viscosity and mass, evaluated quality factors and evaluated resonance frequencies for viscosity and mass density. So these are the measurements including the error bars. And the nice thing is the model completely fits these measurements. And that's not calibrated. I could conclude my talk now, but let's look a little bit closer. The reason why it fits so good is that we investigated here a pretty large range of viscosities. So we did another experiment in a narrower range of viscosities. So the first experiment was from 1 millipascal seconds, which is, let's say, water, up to 200 millipascal seconds. In the second experiment, we took acetone isopropanol solutions, which give you viscosities in the range of 0.2 millipascal seconds to 2 millipascal seconds, and yeah, we had 11 solutions. And as you can clearly see here, we have a slight deviation of the model and the measurements, which we could calibrate. And yeah, now I unfortunately do not have a good message, but two bad ones. As I mentioned before, viscosity and mass density affect both the inertial term and the dissipative term. It means in the worst case, you need 4 calibration quantities, and as the function fails, you do not need 4 factors, you need 4 calibration functions. Okay? So in your model, you introduce empirical calibration functions, and yeah, with these empirical calibration functions, you will be able to fit your measurement, your model into the measurement. But still, there has a lot of work to be done on the calibration, and maybe you find a function which corrects the model, and you end up with because you introduced this correction function in your model, and maybe you end up with the single calibration factor. But this has to be discovered with the huge measurement series. Okay, so let me finally conclude my talk. I showed you that second order models nicely describe resonant viscosity and mass density sensors. However, they might become inaccurate. Complete analytical models allow for modeling all cross sensitivities, and calibration is absolutely necessary if you are aiming at sensors with high accuracies. And in our outlook, of course, as I already mentioned, we have really to focus on this calibration process, and maybe to redesign the sensor to make the calibration of the device easier. Okay, so thank you very much for your attention, and I hope that we have still time for some questions.